derivative. Okay. Is that okay? Okay, so the first blue one is if we only consider the one dimension only on the x. And the second blue one is we consider the k is the constant, so we take it out. Okay, so this is in the cube, so it's xy coordinate. So today we are going to expand a little bit before we run the experiment. So if we consider a cylinder like this, then we only consider along the axis, 考虑它的径向. Okay, so let's roll it like this. Then assume we have the heat going to transfer out of the cylinder. So assume there's a layer inside. Okay, let's draw it like this. There's a layer. So there's a thickness. This actually is what we are exactly the same in the cubit. Then the r direction is in this direction, okay? And if we put it slightly bigger here, let's do it like this. The layer looks like this. So the heat is going to conduct from inside to outside. Okay, so this will be QR, this will be QR plus delta R. Okay, this is similar with the one we draw on Friday. We have a cubit and the heat transferred across the cubit. So it will be Qx and become Qx plus the Q delta x. So this is the same in the cylinder situation. So we take the first law again, then the QR minus the QR delta R plus the heat is going to generate will equal to how the system internal energy going to change along the time. Okay, this is the same one. And don't forget, the heat generation is volumetric phenomena. So the Q generation, we can write it down like this, sorry, times the area times delta R. So this is the area. Okay, so later on we're going to play a little bit of the math, so no reason, just want to modify or rearrangement the equation. So we divide our first equation with the area and the delta R, so you can see, then we'll put the minus in the front, then it will be easier to put the Q delta R to the front, and QR delta R, then this will become Q generation and low C T delta T minus delta T. Okay, so if you happen to miss why the delta U delta T will become the low C and times the time difference. I record this a little bit, so this will become low C, A, delta R, C, oh sorry, low A delta R, because this is N, and C, and this is what I wrote, delta C. Okay. Okay, so now we push the stuff into the limit. So for example, the time difference is very small, approaching to 0. And also the thickness of the ring inside of the cylinder is very small, so the delta is also approaching to 0. Then the old equation will become minus A and partial, now it's partial. Partial R plus Q generation equals to low C partial T partial T. Okay, those are from the calculus, okay? It is the concept of the limit. Okay, we take another page. Oops. Okay. Then if you recall the Fourier law, the Q equals to minus Ka partial T partial R. Then we can put this inside. So the equation will become like this. Okay, and similar to the XYZ coordinate, then we consider the K equals to constant. Then we can take it out the K. And as you can see here, we have area here. Could you just delete it? No, because the area has the function of R. So if I take it like this, so in the cylinder case, then the area equals to 2 pi r L, the length of the cylinder, right? So the A consists the component of the R, and the equation have the relevant to the partial R, so we cannot take out the R, so we'll leave the R inside of the equation. So the equation will become R then we divide the K to make the equation more concise compared with the one we read on the textbook, and then also put the R inside to our equation. Okay? 好，因为 A 里面有 R 的成分，所以我们在我们的偏微分里面有 R 的话，我们不能直接就把 area 直接消掉，所以你可以把2拍 L 的地方消掉，但是你要把 R 留着，好，所以你的 equation 就变成现在这个样子，好，把 R 留在里面。Okay, so this is the case of the cylinder. So what is the case in the spherical? 好，球形坐标。Then the area become 4 pi r squared. Then you put it into the equation as well. So it will become Okay, you might find there's a chance there. So you will see if I increase the dimension, there's only some of the position of the equation is going to change. And we can remind you guys a little bit about the custom coordinate, the XY system, like we just did at the very beginning of the class. Okay, so this is x, y, z coordinate, and then we only consider the one x. Then if you found you substitute the x into the r, then you will find the relationship. Then you can write it down as the governing equation. The order of the r placed into the bottom. Okay, so this will be the general equation going to solve across different dimensions. Okay, so if it's x, y, z system, custom coordinate, then the n will become 0. Then you need to put either x, y, or z. So it's not going to be r, then you put it to x, y, z. But if n equal to 1, there will be cylinder coordinate. Then if it's spherical coordinate, then the n equal to 2. So only one equation, and then sum up everything. But by looking at this equation, you can find this is a PDE, right? So you already learned with the fluid dynamics, so you know the PDE is not easy to solve by hand. You can probably use the MATLAB or something. So only several cases you can solve the PDE. So with boundary condition, with the initial condition. So this Friday we are going to talk about if we include different boundary condition and different initial condition. Then we can solve this heat equation. Okay. So far we already introduced the complete form of the heat transfer equation. Okay, if there's no further objection, I'm going to switch to our design and group discussion. Okay.